Welcome to the Deep Dive. This is where we take sources you send us and, well, really get into them. Today, we're tackling something pretty fundamental. Mathematical knowledge. What is it? And how does it stack up against other ways we know things?
Yeah, it's a great topic. We've got this document, methodsandtools.pdf, that a listener sent in.
Right. And our mission, for you listening, is to pull out the key stuff. What makes maths unique? Maybe even a bit weird sometimes.
Definitely can be.
So, if you use mathematical ideas at work or just find it interesting, they should hopefully give you some useful context.
Okay, so where do we start? That document mentions Raphael's School of Athens. It's a good visual, actually.
Ah, yeah. Plato pointing up, Aristotle pointing down, right?
Exactly. And that picture really captures a core idea here. Plato up there, that's like the abstract world of mathematics, idealized concepts.
Okay, pure ideas.
Right. And Aristotle gesturing down towards the earth that represents the sciences, engaging with the tangible empirical world.
So a basic split. Abstract versus physical.
Pretty much. Mathematics mainly deals with abstract objects using deductive reasoning. Science, well, it's empirical, using inductive reasoning, drawing conclusions from data about the world.
So maths is more top-down logic. Science is more bottom-up observation.
You got it. Deduction in maths means starting with axioms, those fundamental principles, and logically deriving conclusions, like building block by block.
Okay. Each step guaranteed by the last one.
Whereas science often starts with specific observations, collects data, and tries to build up to general laws or theories. Induction.
Right, moving from the specific examples to the general rule. And this must mean the kind of certainty you get is really different, doesn't it?
Oh, absolutely. That's a huge point. Mathematical proof, well, it gives you absolute certainty within its own system once you prove something from the axioms.
It's true, full stop.
Yeah.
Assuming the logic's right.
Exactly. Within that framework, it's definitively true. Scientific knowledge, though, it's always provisional.
You mean it could change?
Yeah. It's based on the best evidence we have now. But new evidence could come along and force us to revise it, or even, throw it out completely.
The document mentions Euclidean geometry here as that kind of perfect, self-contained logical world.
Here's a classic example. Starts with a few postulates, basic assumptions, and everything else. All the theorems flows from those using pure logic. You don't need to go out and measure angles on triangles in the real world to check them.
The internal consistency is everything.
Precisely. That's the goal. Now think about a scientific model, maybe the theory of evolution or gravity.
Okay.
Hugely supported by evidence, obviously. But still, technically, models. They could be refined, maybe even replaced one day if a better explanation comes along.
So proof in science means really strong evidence, not logical necessities like in math.
That's it. Scientific theories can be falsified, tested against reality. Mathematical theorems, if the proof holds up, are solid within their axiomatic box.
This really gets back to those old philosophy debates, doesn't it? Rationalists thinking reason is king, empiricists saying it all comes from experience.
Definitely echoes that. Rationalists saw maths as the prime example of knowledge gained through pure reason, independent of senses. Empiricists, well, they grounded everything in observation.
And Kant came along and tried to sort it out.
Yeah, he made that distinction the document mentions, mathematical truths being sort of analytic true by definition within the system, scientific truths being synthetic, telling you something new about the world based on experience.
Okay, so this quest for absolute certainty through deduction is central. Let's dig into mathematical proof itself, what makes it so special.
Right. The document gives a definition, which is helpful. It's a rigorous logical argument showing a statement necessarily follows from axioms and things already proven.
Necessarily feels like the key word there.
It really is. The aim isn't just persuasion, it's demonstrating logical inevitability, convincing people beyond any doubt purely through the steps of the argument.
Which is way stricter than what we mean by proof in, say, a courtroom or even just everyday life.
Totally different standard. Scientific proof is about compelling evidence, the balance of probabilities. Legal proof, beyond a reasonable doubt, is about persuasion, hitting a certain threshold of belief.
But mathematical proof is about logical consequence. If the axioms are true, the theorem must be true. No wiggle room.
Exactly. It implies necessity. Other kinds of proof suggest strong support, but they're always potentially open to challenge by new information. They're defeasible, as philosophers might say.
The example of 1 + 1 = 2 versus smoking causes cancer is good here.
Yeah, it highlights the difference perfectly. One has a formal logical derivation within a number system.
You can show the steps.
Right. The other, smoking and cancer, is based on overwhelming statistical evidence, biological studies, empirical data. You can't logically deduce it from first principles in the same way.
So, mathematical justification.
Yeah.
Formal, absolute within its system. Scientific justification. Empirical, always potentially fallible.
That's the core distinction. Even the axioms of science, like conservation laws, are really just very well-supported assumptions about reality. They could, in theory, be overturned.
But mathematical axioms aren't tested against reality. They're just chosen.
Chosen, yes, or agreed upon, often for consistency or because they lead to interesting or useful mathematics. Their truth isn't empirical. It's about their role within the abstract structure.
Okay, this idea of maths as this self-contained logical game is clear. But then the document throws a curveball. Counterintuitive results, mathematical surprises.
This is where it gets really fun and maybe a bit mind-bending, because even though it's all logic, maths can produce results that just seem completely wrong based on our everyday intuition.
Like the Banach-Tarski paradox. That sounds wild.
It is wild. The idea that you can take a solid ball, cut it into a finite number of, well, let's call them pieces.
Okay.
And then just rearrange those pieces with no stretching or anything to form two identical copies of the original ball.
Wait, what? How? That sounds impossible. Look, magic. You can't just duplicate volume like that.
Exactly. It completely clashes with our physical intuition about volume conservation. You cut up an apple, you rearrange the pieces, you still just have one apple's worth.
Right.
But mathematically, it's proven to be possible. It's what's called a veridical paradox, seems contradictory, but it's logically sound within the specific mathematical framework it uses.
So where's the catch? How does the logic work if intuition screams no?
The catch lies in the nature of those pieces. They aren't nice, simple shapes we can imagine. They're incredibly complex, fractal-like sets called non-measurable sets.
Non-measurable, meaning they don't have a definable volume in the usual sense?
Precisely. The paradox relies on the axiom of choice, a principle in set theory that allows for the existence of these bizarre sets. So the paradox works because you're dealing with objects that defy our intuitive understanding of measurement.
So it's not the logic that's flawed, it's our intuition, which is based on normal objects, not these weird mathematical ones.
That's a great way to put it. Our intuition is built on experience with the physical world, with measurable things. Banach-Tarski shows that when you step into more abstract realms, relying on principles like the axiom of choice, intuition can fail you.
The document mentions other examples too, like non-Euclidean geometry.
Right, where parallel lines might meet or the angles in a triangle don't add up to 180 degrees. Again, counterintuitive if you only think about flat surfaces, but perfectly logical in curved space.
Or probability puzzles like Monty Hall.
Where the logical answer about switching doors feels wrong to many people initially, these things force us to re-examine our assumptions, the often hidden assumptions baked into our intuition.
And how does a mathematician react to something like Banach-Tarski? Just accept the weirdness because the proof works.
Essentially, yes. The reaction is usually careful analysis of the axioms and definitions involved. If a proof is logically sound, following accepted rules from accepted axioms, then the result stands no matter how strange it seems.
Trust the logic over the gut feeling.
Exactly. It highlights that connection between belief and justification. In maths, justification comes from the formal proof, communally verified, even if it clashes with common sense.
And Gödel's theorems are mentioned too. That's another mind bender, right?
Oh, definitely. The idea that in any sufficiently complex formal system, like arithmetic, there are true statements that you cannot prove within that system itself. It challenges our intuition about completeness, about being able to prove everything that's true.
So these surprises really drive home how much depends on the starting rules, the axioms. Which brings us back to mathematics as an axiomatic system. Can we unpack that a bit more?
Sure. An axiomatic system is basically a structure built on a deliberately chosen set of foundational assumptions, the axioms, plus strict rules for making logical deductions.
Like the foundations and building codes for a house.
Good analogy. You start with things you accept without proof, the axioms and rules about how you can combine them, the rules of inference, then you see what you can build. The document defines it formally as a set of formal statements, used to logically derive other statements.
Euclid's geometry, Peano's axioms for numbers. Those are the famous blueprints.
They are the classic examples, yeah. You define some basic terms, lay down the axioms about how they behave, and then use pure logic to derive theorems. The whole point is logical rigor and consistency.
Right, consistency is key. You don't want the system to contradict itself. And ideally, completeness too. being able to prove or disprove anything within the system.
That's the ideal, yes. But as we just mentioned with Gödel.
Right, Gödel showed that for powerful enough systems, perfect completeness is impossible.
Exactly. Any consistent system containing basic arithmetic will have true statements it can't prove. A fundamental limit. But even so, the axiomatic method starting with explicit assumptions and deducing consequences remains the backbone of mathematics.
Okay, so how does this axiomatic setup in maths compare to other kinds of knowledge? Do sciences have axioms in the same way?
Well, that's where things get interesting. Science has foundational principles, definitely, like conservation of energy, laws of motion. We rely on them.
But they're not axioms in the mathematical sense.
Not quite. The big difference is how they're justified. Scientific principles are accepted because they have massive empirical support, they match observations. But crucially, they could be revised or overturned by new evidence.
They're tested against the world.
Mathematical axioms aren't tested like that. Their acceptance is more about internal consistency, usefulness within the mathematical structure, maybe even elegance. Think about the axiom of choice again.
The one behind Banach-Tarski.
Right. Some mathematicians use it because it's powerful and helps prove lots of other things. Others avoid it because it leads to those weird, counterintuitive results. There's a freedom to choose or debate axioms in math that you don't really see in science.
Because the goal isn't necessarily to describe physical reality in the same way.
Exactly. Maths values internal logical coherence, rigor. Science values explanatory and predictive power about the real world and accepts a certain level of uncertainty as part of the deal.
So we judge a mathematical theory by its internal logic and a scientific theory by how well it matches reality.
Broadly speaking, yes. Which connects to ideas about objectivity. Maths is often seen as highly objective. The results should be the same for anyone following the rules.
Whereas fields like history, ethics, much more room for perspective interpretation.
Definitely. You might have ethical principles that act a bit like axioms, like maximize well-being, but they're normative about what should be done, not logically derivable truths about how things are. They come from values, not pure logic.
The document mentions other systems too, like ideologies or religions, having core beliefs. But again, the justification is different, based on faith or tradition, not logical proof from axioms.
Right. The method of building knowledge is fundamentally different. Although you could argue that even in science or law, there are foundational assumptions that function like axioms sometimes.
But the key thing in maths is making them explicit and sticking to them rigidly through logic.
That seems to be the defining feature, yes. Laying the cards on the table with your assumptions and following the logic wherever it leads.
Okay, let's shift to the language itself. Mathematical language, with all its symbols. It's pretty unique.
It really is. It's this hybrid thing, isn't it? Part natural language, part specialized jargon, part pure symbols.
The document calls it an extension of natural language for precision.
Yeah, that's a good description. It aims for concision, precision, and removing ambiguity. That's the goal.
We use ordinary words, like group or field or ring, but they mean very specific things in maths, often unrelated to the everyday meaning.
Totally. Or think about simple words like or. In everyday talk, it's often exclusive tea or coffee. In maths, it's usually inclusive A or B means A or B or both. That precision matters.
And then you have the symbols, things like or, for all, or a, there's this. They pack a lot of meaning into a small space.
They function like highly specialized words with universally agreed meanings within the system. Unlike natural language words, which can shift meaning with context or carry emotional baggage, these symbols are meant to be rigid and unambiguous.
Pi is pi everywhere.
Exactly. The goal is universality and clarity, to strip away the fuzziness of ordinary language and get down to the pure logical structure.
So it's a language built for expressing abstract ideas with maximum precision.
That's the essence of it. It's incredibly powerful for that reason. You can express concepts in mathematical notation that would be incredibly cumbersome, maybe even impossible, to state clearly just using everyday words.
Okay, last big area. Personal experience. How does that fit into maths, which seems so objective and impersonal?
Yeah, that's a really interesting contrast. In fields like the arts, ethics, even history, personal experience and perspective are often central, right?
Definitely. How you feel about a piece of music or your interpretation of a historical event.
But maths, going back to that Plato image, is often seen as existing independently of us. A theorem is true whether you or I believe it or what our background is. 2 + 2 + 2 = 4 doesn't depend on feelings.
It aims for objectivity. Two mathematicians, same axioms, should get the same result. Ideally.
That's the ideal. Now, that doesn't mean personal experience plays no role. The document rightly points out that intuition, visualization, playing with examples, these are crucial for discovery.
So the aha moment might come from a personal insight.
Absolutely. Mathematicians talk about intuition guiding them, seeing patterns, having a feel for the problem. That's often driven by years of personal experience working with mathematical ideas.
But that's not the proof.
Crucially, no. That's the motivation, the spark, the hypothesis generation, the justification, the thing that makes it accepted mathematical knowledge has to be a formal, logical proof that others can check and verify.
It has to be communicable and verifiable by the community, not just a private revelation.
Exactly. Unlike maybe a mystical experience, mathematical insight has to be translated into that rigorous impersonal language of proof. Think of Andrew Wiles proving Fermat's last theorem.
Right, years of intense personal struggle for him.
Deeply personal journey. But the proof itself had to stand up to intense scrutiny by other experts, checking every logical step. Its acceptance wasn't based on his personal conviction, but on the verified rigor of the argument.
So maths values this objectivity. It's like a second language anyone can learn, separate from individual viewpoints, unlike fields where perspective is key.
So while personal experience fuels creativity and discovery, the foundation of mathematical knowledge remains rooted in that formal reasoning and impersonal standards of proof.
Okay, let's try and wrap this up. What are the big takeaways?
Well, I think we've seen math stand apart. It's defined by deductive reasoning from axioms. It aims for absolute certainty through rigorous proof.
Right, within its own logical system.
Exactly. It uses this incredibly precise symbolic language to avoid ambiguity. And sometimes it leads to really counterintuitive results, like Banach-Tarski, which actually push us to understand its foundations better.
And ultimately, justification rests on that formal logic, that communal verification of proof, rather than personal experience or intuition, even though those play a role in discovery.
That sums it up pretty well. Understanding these distinctions, well, it gives you a clearer map of knowledge itself, doesn't it? How different fields work.
Yeah, and hopefully for you listening, it sheds some light on any maths you encounter, seeing where it comes from and what makes it tick.
Yeah.
So here's a final thought to leave you with. Think about a time your gut feeling, your intuition, told you one thing pretty strongly.
Okay.
But the logic, or maybe the evidence, pointed somewhere else entirely.
Mm-hmm.
How did you handle that? How did you reconcile that conflict?
Yeah, that tension.
Thinking about how mathematicians trust formal proof, even when it feels weird, offer any clues for navigating those kinds of situations in other parts of your life or work?
That's a good question to ponder. Definitely something to think about.
Thanks for joining us for this deep dive.
My pleasure. Thanks for listening.